This is problem 40 from electric circuits. Assuming the capacitor is initially uncharged and the switch is closed at time t is equal to 0, the current through the resistor in the simple RC circuit at right can be modeled by this equation. Based on this result, determine the following as functions of time. In part A, we want to know what the potential difference across the resistor is. Well, they give us the current through the resistor, and by Ohm's law, we can say the potential difference across the resistor is equal to the current times the resistance. And so we have the current here. So this is V divided by R e to the negative t over RC times R. So that's just equal to V times e to the negative t divided by RC. We want to know the potential difference across the capacitor. Well, if we sum up the potential differences around the closed loop, we must get 0. So V from the battery must be equal to the change in potential across the resistor plus the change in potential across the capacitor. Therefore, delta VC, if I bring the delta VR over to the other side of the equation, I have V minus delta VR. And I have delta VR up here, so I'm just going to take this and plug it in down here. And I have V minus V e to the negative t over RC. And then I can pull the V outside and say V minus e to the negative t over RC. Then I want to find the charge on the capacitor. Well, the potential across the capacitor is equal to Q divided by C. So I can just take my expression here for delta VC and divide that by C. So I have, actually, I want to find the charge on the capacitor. So I would say the charge is equal to C times delta VC. So I take this and multiply it by C, and I get C times V is equal to 1 minus e to the negative t over RC. Then I want to find the energy stored in the capacitor. Well, this equation, I believe, is given to you in the beginning of this section in the Spiral Physics textbook. This is on page 5 of the Spiral Physics textbook. We have the equation for the energy here. So I have U is equal to 1/2 times C times delta V squared, where this delta V would be the potential across the capacitor. So that's what I found up here. So I can take that and plug it in here. So I have 1/2 times C, and then delta VC, that's equal to V times 1 minus e to the negative t over RC squared. Let's write that as 1/2 times C times V squared times 1 minus e to the negative t over RC squared. Then I want to find the energy converted by the resistor. The energy converted by the resistor would be the power. We should have an equation for that in the beginning of this section also. So here it is on page 4, and we have an expression for the current, and we have an expression for the change in potential across the resistor. So to find the energy converted by the resistor, we would say the power is equal to the current through the resistor times the change in potential across the resistor. And so I'm going to take the expression for the current, which they gave me up here. So I have V divided by R times e to the negative t over RC. That's the current, and then the potential across the resistor, I found that in part A. So I can plug that in also. That's V times e to the negative t divided by RC. And then if I simplify that, I have V times V, that's V squared, divided by R, and then e to the negative t over RC times e to the negative t over RC is e to the negative 2t divided by RC. And that concludes problem 40.